All right, so number one of test number 4, we're now recording. Light traveling at 3 times 10 to the 8th meters per second has a frequency of 6 times 10 to the 15th hertz. What is its wavelength? Now remember, speed or velocity, very simple. It's frequency times wavelength. So your velocity is 3 times 10 to the 8th meters per second. Hertz is seconds to the negative 1 power. So 6 times 10 to the 15th seconds to the negative 1 power, and then times lambda. So if you solve for lambda, and if you do it correctly, the final answer will be in meters. 3 over 6 is kind of a zone fraction. 10 to the 8th, oh, 10 to the 15th, my bad. Let's fix that. So it's 0.5 times 10 to the negative 7 power. Or you could move that over, because 0.5 is 5 times 10 to the negative 1. So it comes 5 times 10 to the negative 8th power meters. So the answer is going to be that one right there, 5 times 10 to the negative 8th. So that's number 1. Clear? Move on. Okay. How much current does a 6-watt light bulb draw if it operates at a voltage of 120? So P equals IV. Oh, and formulas. I will actually update the formula sheet and highlight the ones that will be relevant for the final exam. So make sure you guys have access to that. So I times 120, your I is 0.5 amps. Easy peasy. That's it right there. I'll keep moving. Okay, a lot of people had a hard time with this question. And a lot of people put 2 as their answer. Maybe I made a mistake, I don't know, but let's work through this one. So here you have actually 1.5 cycles, because that's one cycle. That's one cycle right there. So 1.5 cycles is going to equal 0.6 meters. So if I divide by 1.5, divide by 1.5, one cycle or one period is going to be 0.4 meters if you use a calculator. And remember, we talked about velocity equals your frequency times your wavelength. Your velocity is 0.5. Frequency is what we're trying to solve for, right? Actually, no, we're trying to find the period. But we need frequency first. So your frequency is going to be 0.5 over 0.4, or 1.25. And it's seconds to the negative 1 power. Now, period, which we call capital T, is 1 over F. And by the way, this down below is the length, not the actual one period, but the length of one period. T equals 1 over F, so it's 1 over 1.25, which would be 0.8 seconds. So that's the answer. The answer is 0.8 for this one here. So I'm not sure you guys got 2. Maybe you guys thought you just flipped that over, thought that was frequency. But you know, yes, you do flip over frequency, but I didn't give you frequency. You had to first figure out the wavelength, then use the velocity formula, get the frequency, and then do 1 over that. So it was actually kind of a 3-step process there. Any questions about that one? All right, let's keep moving. Okay, circuits. Some people still have a little trouble with this. So you're asked to compare the current resistor A to the current resistor B. What you could do to make your life a little easier is just make each of these 1 ohms. And these are parallel, so you have to do 1 over 1 plus 1 over 1 plus 1 over 1 equals 1 over the resistance of a parallel circuit, so that becomes 3. So the resistance of parallel circuit is just going to be 1/3, where that was 1. So clearly A is 3 times as much. So the answer is 3 times as much for that one. Actually, let me double check the answer key, because I think I may have actually put 9 as the answer. I don't know, but it should be 3 times, unless I'm missing something here. Oh, the current. Sorry, my bad. Sorry. It's not the resistance. My apologies. Okay, we're not done yet. Okay, let's say the voltage was 1 volt and V equals IR. So 1 equals I times 1 as I'm passing through A. So my current will be 1 ampere. Then what's going to happen is that the combination is this 1/3 of BCD. So voltage of BCD and the current of BCD times its resistance, that resistance is 1/3. So the current that passes through, actually, hold on a sec here. Oh, shoot. Okay, I'm really just screwing this one up hard. Okay, let's backtrack a little bit. Okay, my apologies. I'm just messing this one up pretty terribly. Okay, we actually need to get the total resistance. Okay, so again, 6 resistors, they're all identical. So the resistance of BCD, I was correct about that, was 1/3. And you have all the other ones in series. So you have 1 plus 1/3 plus 1 plus 1. So that's going to be actually 3 plus 1/3 or 10/3. So that's the actual true total resistance. Okay, let's say our voltage was 3 volts. So for current A, V equals IR. So you have 3 volts. And then what's going to happen, excuse me, is that you're going to solve for the current, which is, of course, going to be 3 amps. Okay, the 3 amps will get split equally over here. And so what that means is that that's going to make the voltage of each of these 3 volts, which was what it should be. And then, oh, wait one sec. Okay, I'm screwing this one up again pretty hard. Okay, the resistance is 10/3. We're doing 3 volts, so the current is actually 9/10. So 3 volts, so current's 9/10. So this sees 9/10 amperes. Now it's still going to get split. So BCD is 1/3. So 9 times 1/3. So you actually can get the voltage there. 3/10 of a volt. But what's going to happen is for BCD, the combination of those. And the resistor, the combined resistance of BCD is 1/3. However, now you have the voltage for each of those. 3/10 equals I times R, and your R is 1. So the current's still going to be 1/3 of what it was before. So yes, the answer should be 3 times as much. So I had that right. Sorry, just really roundabout with my explanation here. Let me actually end this preview. Just make sure I didn't mess up the answer key for that one. Yeah, 3. So anyway, let's Now go back to the preview. Okay, let's go to number 5. Okay, number 5 is dealing with Doppler effect. So the frequency of the observer equals the frequency of the source times the velocity of your sound wave, or velocity of sound, plus or minus the velocity of the observer, and velocity of the sound wave minus plus the velocity of the source. Well, the frequency of the source is 600 hertz. The velocity of sound wave, assuming is 340. You are stationary, and it's going away from you. So if it's going towards you, use the top sign. It's going away, do the minus. So minus 0 over 340 plus the speed of the car, which is 20. So since it's going away from you, you gotta use the bottom signs. So it's 600 times 34 over 36, because you get 340 over 360 over here. And if you work on the calculator correctly, you should get 567. Yeah, so you get 567 for that one. So that's this choice right here. Okay, we'll keep moving. Okay, I promise I will do better with this circuit problem. So you just want the total resistance. That's parallel. So it's 1/12 plus 1/4, which is 1/12 plus 3/12, which equals 4/12, which is 1/3. But you got to flip it. So RP is 3 ohms. So that counts as 3 ohms. Then these are in series. So that becomes 6 ohms, and you got 3 ohms down here. And then finally, you have 2 that are parallel. 1/6 plus 1/3. That's 1 over RP for parallel. 2/3 is 2/6. Sorry, 1/3 is 2/6. So 1/6 plus 2/6 is 3/6, which is 1/2. Flip that bad boy over, you get 2 ohms. So that's D for that one. So that's my component our final exam. I think that one's kind of fair. I think the other one I just did was a little bit tough. So hopefully that's okay. And I like that Doppler effect prop. That was a good one too. Okay, torque. It's very perpendicular, the force compared to the lever arm. The lever arm's a wrench. So you don't have to use any sine theta stuff. It's just force times distance, or force times radius. That's torque, right? We know this. Well, your force, guess what, is 20 newtons. But you got to convert this, because all these are in meters, to 0.2 meters. So it's going to be 4 Newton meters. That's why it's going to be that choice. Keep trucking along here. Yeah, select all that apply. If you're moving constant speed in a circular path, so here's that you have a particle that's kind of going in this direction. So the velocity is not constant because you are changing direction. So velocity will not be constant here. And also the acceleration is not constant because, again, you're changing direction, because acceleration is also, because if the direction is changing, so is acceleration. But that is true. The net force is non-zero, because remember, net force is mass times acceleration. And you do have acceleration happening here. So that was the only choice that worked, was that one. So it was a little tricky. Even if you're moving at constant speed, it is a circular path, so you are changing direction. So velocity is not constant. And the acceleration, well, the acceleration could change. Actually, come to think of it, that one might be, well, actually depends. Because centripetal acceleration, I should have been a little more clear about this, is v squared over r. Because velocity is changing, yeah, I don't think you can say the acceleration is going to be constant for that one. That one's a little tricky. But I think it'd be partial credit if you got part of that right. Over here, okay, a lot of people thought the answer was this one. And it's not. So actually, that's not true. Here's what's happening. Do you want the object's angular speed? So what you really want to do is know your formulas well. So let's go over here. Click on exams. Test number 4. Formulas for test number 4. And you're going to want to use some of these formulas that you see over here. So again, we know acceleration is v squared over r, and v is r omega, and acceleration is also r omega squared. But if you wind up using that, you should have enough information to figure out this problem. So let's work through it. So the centripetal acceleration, is that right? And centripetal acceleration is v squared over r. And you want the object's angular speed. So r times omega squared. So you're squaring that. Remember, v equals r omega. Your centripetal acceleration is 9. You have r squared times omega squared over r, which they cancel, so it becomes r omega squared. Your r is 0.25. So 0.25 knows 1/4. 9 equals 1/4 times omega squared. Omega squared is 36. Omega is 6. That's why it's going to be that. So yes, I didn't give you velocity, but you didn't need it if you use these two formulas correctly and did a substitution correctly as well. Let's keep moving. Okay, number 10. Yeah, this one was a big problem here. So we're going to spend a little time on this one. So solid sphere, that mass and radius, and I give the radius in centimeters, so be careful there. Slipping without slipping, rolls down 30-degree incline that's 8 meters long. So I do ask for the initial potential energy, the inertia, the linear speed, and the angular velocity. Part 2 is worth the most points. Just so you know, that was worth 2 points. That was worth 2 points. That was worth 6 points. And that was worth 2 points. Now, the crappy thing with the system of Schoology is that it's going to give you 0 out of 12, even if you got 3 of these 4 things right. But don't worry, I looked at it. I try to give you credit. If you submitted work, then of course I was able to help you out. Because if you probably missed one little part, it kind of skewed your answers down the road. But it's okay, because I was able to figure out what you did wrong and give you the proper credit. But here's, yeah, go ahead.
It said it was worth like 28 or something like that out of 100
points.
Yeah.
Oh, that's when you make the adjustment afterwards.
Okay.
Yeah, that's to make up 100 points. Yeah, no, it was 20% of the exam, yes, which I think is justified given how involved this problem was. But yeah, but it was 12 out of 44. So yeah, I guess that comes out to 28.
Gotcha.
So here's the ball. It's rolling down the incline. Okay, so I probably would just start off with this, the initial potential energy plus the initial translational kinetic energy plus the initial rotational kinetic energy, which are actually both 0. Then final potential energy, which is 0, because you're down the hill, plus the final kinetic translational energy, which of course is not 0, and the final rotational kinetic energy, which also is not 0. But so we know these are 0. That's going to be mgh. That's 0. That's going to be 1/2 mv squared plus 1/2 I omega squared for the rotational kinetic energy. So you just do that right away. That kind of clears things up. So this one, initial potential energy is mgh. Your m is 1 kilogram. G, I told you to use 9.8. And the height's off the ground. You're going to have to figure that out. It's not that hard, though. If you use some simple trig, that's 30 degrees and that's 8. That's going to be 4 meters, just so you know. And that's 4 root 3 meters. If you just use basic SOHCAHTOA rules, because sine 30 degrees will be your height over 8. So your height's going to be 8 times sine 30 degrees. Sine 30 degrees is actually 0.5 if you plug it in your calculator. So height's just 4 meters again. So that's all you're plugging in. You're doing 4 times your mass times your acceleration due to gravity. And I said around the 1 decimal place, you should get 39.2 joules. Then to get the inertia, well, we have the formula, which is 1/2, actually just I, sorry, just want the inertia. So you're going to do 2/5 times the mass, which is 1, times the radius, which is 0.2, mind you, not 20. You got, because I asked for the meters. So 0.4 times 0.2 squared, and it's 0.016. By doing this, this will help us figure out the answer for part C. So we go back to the conservation equation below. 39.2 equals 1/2 times 1 times v squared plus 1/2 times your I, which is 0.016, and omega squared. Now remember, omega times r equals v. So remember, that's one of our formulas. Omega times r equals v. So omega is going to be v over r, and our r is 0.2, so that's going to be v squared over 0.2 squared. If you worked all that out correctly, 39.2 equals 0.5 v squared, 0.016 divided by 0.04 times 0.5, so that becomes 0.2 v squared. So you said to be careful. I think that's where some people kind of made a mistake. Maybe they just look up a point, not a big deal. 39.2 divided by 0.7. Square root it. So you have 7.48 meters per second. Then to get the angular velocity, just divide by r. So I'll just work 2 points. So r is, remember, is 0.2. And you get 37.42 rads per second. So that's how number 10 works itself out. Hopefully that wasn't too bad. That was kind of the epitome of week 5, using inertia, conservation of energy. Let's kind of go back to old stuff. Rotational kinetic energy, realizing that you have all that happening. So yeah, and remember, if it's not rolling, then you don't use rotational kinetic energy. If it was rolling, some portion of kinetic energy is attributed towards rotational. Okay, let's keep moving. This one here, I think, went fine. Which coin is inversely proportional to the square root of the block's mass? So we do have a formula for that. Frequency, I think, was, I should know this. Just use your formula sheet, make it easy. Yeah, it's 1/2m times root k over m. Sorry, 1/2 pi, duh. Sorry, 1/2 pi. That's what I was forgetting. So you can kind of break it off like this. So f times root m equals 1 over 2 pi times root k. Well, all that is just a constant. And it's being multiplied together. So that's why they're inverse proportional. So it's inverse proportional to the square root of frequency. Sorry, the mass. So which one is inverse proportional to the square root of Bloch's mass? Frequency. There we go. Lastly, number 12. So wheel a moment of inertia that starts from rest and accelerates under constant torque for 8 seconds. What is the wheel's rotational kinetic energy at the end of 8 seconds? So remember, rotational kinetic energy is this: 1/2 times I times omega squared. Now the problem is that we don't know what omega is. We do know our inertia. That's easy. It's like I told you, it's 5. But now to get omega, what you're going to have to do, now remember torque does equal I times alpha. That's another formula we have. So again, your formula sheet's your best friend. Yeah, torque's I times alpha right there. So right here. So your torque is 3, and of course your inertia is 5. So your alpha is 0.6, and that's rads per second squared. Now alpha is a difference in omega over time, and you're starting from rest. Your initial omega is 0, so omega over 8 seconds, and again your acceleration was 0.6. So your omega is going to be 4.8. That's the final omega. And that's what we want. So it's 1/2 times 5 times 4.8. So if I work that out, I should get 12. Wait. Oh, I forgot the square. Duh. 4.8 squared. Let's try that again. Times 2.5. Yeah, I get 57.6 joules. So that's something I could put in the final exam as well. Something like that, just to make sure you guys are using your formulas correctly. So hopefully that went okay. Any questions? No questions? Okay. So let me stop sharing. So now let's talk about the lab groups. Here are the groups I've decided to put together. Hopefully you guys are okay with them. So let me stop sharing.